But yeah. Yeah, that's okay. I guess they have rats. Yeah, testing or is it part of this? I would go for it. Every single right. I like possible. So you just random this. You're all all right. I hope you're all doing well. Had a good weekend and all that stuff. So what I want to do today is I want to continue with the discussion that we started last time. And there, what we were just starting to do is to talk about how all of the stuff that we're going to talk about in this course about circuit analysis and all these things, they all have their foundation in electricity and magnetism, the stuff that we did in Physics 121. So something that we were able to do is able to show a connection between the relationship between potential difference or voltage difference, which we'll use all the time in this course, and electric fields, and to connect that to a more fundamental theorem of physics, the work kinetic energy theorem. The other thing we did is we just looked at a current going through a conductor or a resistor, and we we use Ohm's law, just the voltage difference across this thing is going to be I times R, but we paid special attention to the sign of that voltage difference, right? So one side's going to be at a high potential and one side's going to be at a low potential, and we want to know how can we figure out which one is high and which one is low based on the current direction. And what we established is if you cross your conductor or resistor in the same direction as the current, you're losing voltage. And if you think of that, it makes a bit of intuitive sense as well, because the current or these charges have to flow through this resistor, which is opposing their motion. And so it's taking energy away from these moving charges. And so you're losing potential energy or a related concept voltage as you go across. So when you cross a resistor in the direction of the current, you lose voltage. The voltage difference is going to be minus I times R. On the other hand, if you cross that resistor anti-parallel to the current, you're going to gain voltage of plus 5 times R. Okay, so what I want to do today is I want to start talking about capacitors and inductors. Capacitors is going to be more review. I'm not going to re-derive everything. I'm going to give you a flavor of how we got those results. And then the inductors, that inductors are solenoids, so we know something about solenoids, but maybe in the context of circuit analysis, maybe not so much. So we'll do that one a little more carefully. Okay, so actually that's a good reminder. I realized that on the first day of classes, I didn't have the Zoom set up to do recordings. And so there's no recording of the first class, but I've made sure that all of the future Zoom sessions will be recorded. So this one and future classes will go on YouTube. Okay, good. So capacitors, by far the most common type of capacitor is the parallel plate capacitor. And it is exactly as it sounds. We're going to take two conducting sheets and we're going to place them in parallel with one another. So here's one. I'll make it a square. It doesn't have to be a square. It could be a circle or any other geometry that you like. And then I'm going to make a second plate and I'm going to place it in parallel with the first one. Okay, and we'll call the distance between these plates D. And we'll say that each plate has an area A. And what we're going to do is we're going to put equal but opposite charge on these two plates. And you could do that very easily just by taking a battery and connecting, say, the top plate to the positive terminal. If you did that, you would get some charge plus Q on that top plate. And you would get negative Q on the bottom plate. So if these two plates started out neutral, you think of it this way and you connect the battery, what's going to happen is the battery is going to cause electrons from one plate, say the top plate, to migrate over to the bottom plate. And so as you take an electron away from the neutral top plate, you end up with an excess of positive charge from the nuclei that make up whatever that conductor is. And then that electron gets deposited on the bottom plate, and so you get excess negative charge on the bottom plate, and they have to be equal and opposite. We know that electric fields point from positive to negative charge. As we saw that in the first class, we said high potential to low potential is the direction that electric fields point. The way you make a region of high potential is to have like some collection of positive charge. So we're going to have an electric field between the two plates of our capacitor. And so I'll draw some of those field lines. And so here's the electric field E. Okay. So what we want to do is we want to come up with a way to characterize the so-called capacitance of this thing. Now, capacitance by definition is the following. So capacitance is defined to be C is Q over delta V. I'll put an absolute value sign over delta V just to emphasize that what we're going to do is we're going to imagine measuring the voltage across these plates. So if we did connect this to a battery, say like a 9-volt battery, then that voltage is fixed. That's 9 volts from whatever the battery supplies. We know that there's a relationship between potential difference and electric field, and we'll make use of that in a second. One way to think about a capacitor is, the common way is that it's a charge storage device. So for a fixed voltage, the charge that you're going to store is C times delta V. Okay, and so the bigger you can make C, the more capacity you have to store this charge. And so that's absolutely true. what we're gonna find is that capacitors do much more than just store charge. In this course, we're gonna find that they are really important components in filters, specifically. So let's suppose that you're gonna detect some experimental signal that's operating at some frequency, but then there's like interfering noise at other frequencies. You can design filters that will pass the frequency that you want and then attenuate all the unwanted frequencies, and capacitors are critical components in designing these filters. And we'll see that in a week or two or something like that. Okay, so I just want to remind you that we can use Gauss's law to find the electric field due to a sheet of charge with charge per unit area. Sigma, Greek letter sigma, is what we use usually to denote charge per unit area. If we just take the charge on a plate Q divided by the area of the plate, that is sigma. So sigma is just the total charge on a plate divided by the area of that plate. So I don't expect you to remember Gauss's law, not all the details anyways, and I won't ask you in this course to apply Gauss's law, but I just want to emphasize this connection with electricity and magnetism. So Gauss's law, remember, was this E dot dA was going to be equal to Q enclosed over epsilon naught. And so what we had to do is we had to define a Gaussian surface, a surface that encloses some amount of charge. That enclosed charge is this Q enclosed here. And then we have to try to evaluate that integral. That's only easy to evaluate if we have like a geometry where the electric fields are, say, perpendicular or parallel to our areas. But we can do that in this case if we had our sheet of charge. Just this could be the top plate or the bottom plate, it doesn't matter. And we can make a Gaussian surface that intersects our sheet and then goes underneath it like so, something like this. Okay, if this was, say, the positive plate, we'd have positive charge here, and we would have electric fields that were pointing upwards above the plates. Oh, sorry, that one's not great. And then they would be pointing downwards below the plates. Okay, so I'll draw a few of those. So there's our electric field. The way we would do this is we would say that our Gaussian surface has a certain area A, and the way we define the direction of the area is it's perpendicular to the area. So it's pointing up from this top plate. And so that means our dA and our electric field are parallel. When you take the dot product with parallel vectors, remember dot product E dot dA is E dA cos theta. Theta is the angle between the vectors if they're parallel. Theta is 0. And so cos of 0 is going to be 1. And what you end up finding out is that 2E times A is equal to Q enclosed over epsilon naught. But Q enclosed is the charge per unit area times the area of that top surface. And then we still have to just divide by epsilon naught. And so therefore we have 2EA is equal to sigma. Sigma is the charge per unit area. Then we have the area divided by epsilon naught. You can cancel those things. Why is there a factor of 2 here? Does anyone know? Who remembers? Yeah, that's right. So we have the electric field penetrating through this top surface of our Gaussian surface. And then also there's the bottom surface where we have an equal amount of electric field crossing that surface. Exactly. Okay, so then what we end up with is E is equal to Q over 2 epsilon naught times K. So that's the electric field. This is the, so sorry, there's something wrong here. Q enclosed. Oh, sorry. Q enclosed is sigma A. Sorry, I'm just going to, I'm just going to leave this as sigma A for now. And what we'll do is we'll cancel the A's here. What I have is correct, but I just want to rewrite this in a more standard way. So this is what you'd usually see for the electric field. Of a uniformly charged sheet. Okay. What I want to do is I want to be able to go back and use the definition of capacitance, Q over delta V. I have the electric field, so I could calculate delta V. But there's one subtle difference. If I had my two sheets, I'll draw them again, positive one and a negative one. Each sheet is going to make an electric field that's equal to this sigma over 2 epsilon naught. Okay, so we'll have positive here and negative on the bottom one. So the question is, what's the total electric field between the plates? Yeah, it's just someone spit it out. Sigma over epsilon naught, right? So the idea is that the top plate between these two contributes an electric field down that's equal to sigma over 2 epsilon naught. The bottom plate also, because it's negative, it has electric fields pointing towards it. And so it also makes an electric field between the two that points down. And it's equal to sigma over 2 epsilon naught. And so we have two contributions of sigma over 2 epsilon naught. If we add them up, that factor of 1/2 goes away. And we would say that the electric field between the plates is E is equal to just sigma over epsilon naught. Okay, what about the electric field up here? What's it going to be equal to? What's the direction of the electric field due to the positive plate above here? Up or down? Up. What's the direction of the electric field due to the negative plate in this region? Down. So they're in opposite directions. Notice that this expression, it's a little bit surprising, but it doesn't depend on where you are in space. So this electric field is constant. It's the same value here. So the electric field due to the positive plate is the same here as it is here, as it is here, as it is here, and same for the negative plate. And so outside these plates, the electric field is 0 above, and the electric field is 0 below. Okay. So anyways, we have the electric field between the two plates. Remember, they're separated by a distance d. And so if I want to calculate the voltage difference between these plates, it's going to be this E dot dl. So this is the voltage difference between the plates. Okay, so what I'm gonna do is I'm gonna pick a path that starts here. So we'll start at point 1. So we'll start at 1, and then we'll follow a path down to the bottom plate 2, and we'll go in this direction from top to bottom. And so if I follow this path, the total length that I'm going to travel is d, the separation between the plates. I'm going to be always moving parallel to the electric field, so the dot product is going to go away. E is a constant, so it can come outside the integral. And if you evaluate this, it's just going to be E times the distance d. I'll make this an absolute value sign. Let's not worry about the sign right now. And E is sigma over epsilon naught. And sigma is the charge per unit area. And so there's a factor of epsilon naught, and there's a d here. Okay, so this is the absolute value of the voltage difference across the plates. And so here you can see that if we increase the voltage difference, we have to also increase the charge. And so more voltage means you store more charge. Okay, so then by definition, C is Q over delta V. And so let's see, Q, we divide by delta V, so we have an epsilon A divided by D. And so this is the familiar result for the capacitance of a parallel plate capacitor. So parallel plate capacitor, I don't know, capacitance. All right. What I want to do is I want to collect some results here. So let's do a little 2-line summary of what we know. The voltage difference across a resistor is I times R. Okay, we'll put an absolute value sign. Let's just not worry about signs right now. Now, the voltage difference across a capacitor is going to be, well, let's see, delta V, bring it over here, divide by C. So it's Q divided by C. But Q and I are not completely independent. How are they related to one another? What's the relationship between the two? Yeah, that's right. So we could write this as R dq dt. All right. What we're going to do next is we're going to talk about the inductor. We have a voltage that's proportional to Q. We have a voltage difference that's proportional to the first derivative of Q. What might you guess we're going to find for the voltage difference across a inductor? Just looking at kind of what we have so far. Doesn't matter if you. Yeah, I just want to guess. We're gonna have a solenoid, a coil of wire, and we're gonna calculate the voltage difference across it. We found one that's proportional to Q, one that's proportional to derivative of Q. So what could it be? It could be. What we're actually gonna find is we're gonna find, that's a good guess. We're gonna find it's the second derivative. Yeah. Okay, good. So the reason we're doing this is because this will be a nice segue into our first little topic is, you know, if we have circuits that involve only resistors and batteries, then we end up with just voltage differences that are I times R, and we can just solve those relatively easy using Kirchhoff laws, and that's the sort of thing we did in first year. if you start having more complicated circuits that involve resistors and capacitors, now you have things that involve charge and the derivative of charge, and so that's a differential equation. We're gonna have to develop techniques to solve that problem. Okay, and so that's where all of this is leading. Okay, so inductors, sometimes also called solenoids, and these are just coils of wire. What's neat about everything that we're talking about so far, a resistor is literally could just be a chunk of metal, right? There's nothing to making a resistor. It's just a chunk of metal that passes some current when you apply a voltage across it. Capacitors literally are just parallel conductors. Very easy to make. Inductors are literally just a coil of wire. And so if we imagine that we just had like some plastic cylinder or something, the plastic doesn't do anything. It just provides something for us to wrap our coil of wire around. So I'm just imagine I take my wire and I just start wrapping it around my little cylinder. And again, the cylinder serves no purpose other than to provide something to wrap our wire around. Let's just make pick a direction for the current in our wire. Okay, and so here's the current I. It's going up behind the cylinder and then coming down in front of the cylinder. Okay, we know that current is a source of magnetic field, right? Charge is a source of electric field. Moving charge or current is a source of magnetic field. And so what we can do is we can figure out the direction of the magnetic field inside the solenoid. It's going to be left or right. Which way is it? Right? How do you know that?
The right-hand rule.
Yeah, there's a right-hand rule for these currents. So you curl the fingers of your right hand in the sense of the current. So in this case, current's coming down in front of this cylinder, and my thumb gives the direction of the magnetic field, and that's correct. It is to the right. And so there's a magnetic field that's going through the center of this solenoid. And so it's passing through here. I'm not going to go through the argument, but just like for the capacitor, we said that there would be a magnetic field between the plates, or sorry, an electric field between the plates of the capacitor, but it was zero outside. It's also true that the magnetic field is zero outside of the solenoid, but non-zero just between the windings, like going through the solenoid. Okay, let's give this thing a length. Let's say that this thing has a length L. Okay, good. Our goal is going to ultimately be to try to calculate the voltage across this solenoid. Okay. If you wanted to calculate the strength of this magnetic field, how would you do it? We used Gauss's law for the capacitor. What did we have for magnetic fields? We are going to use Faraday's law, Ampere's law. Ampere's law was the one that we could use to calculate magnetic fields. Ampere's law said that the integral of E dot dl around a closed loop was equal to mu naught I enclosed. Again, I'm not going to expect you to remember this or to solve these types of problems, but I do want to show you. I want to remind you of where all this stuff comes from. So to do Ampere's law, the first thing we do is we pick a little loop and we go around this loop and evaluate B dot dl. Outside here, B is 0, so this outside part of the loop does nothing. Here, these side edges, B is either 0 or it's perpendicular to the direction dl that we're moving. And what happens when you take the dot product of perpendicular vectors? 0. So these three sides contribute nothing to this integral. It's only this inside piece. And so we would have B times whatever this length is. So B times L is going to be equal to mu naught times I enclosed. I enclosed is the number of times the current, it's the total current that passes through our loop. The way I've drawn it, our coil passes through the loop 3 times. And so we would get 3 times the current. We would divide that by the length to find B. And so we'd end up with the number of turns divided by L, the number of turns per unit length. And that's the classic result for a solenoid. The magnetic field is going to be mu naught, a constant, times the number of turns per unit length times the current. So the N times I is the I enclosed. The L came from this integral, and I just divided it in there. And so this is the magnetic field inside a solenoid. Or in electronics, we would more likely call this an inductor. All right. Now, you've already mentioned Faraday's law, and Faraday's law is very useful. That's something we're going to use. What does Faraday's law tell us? What happens if you have a magnetic field that's changing through a loop of wire?
It'll make a current.
Going to make a current. So Faraday's law tells us about induced voltages that drive these currents. Okay, and so that's what we want to use next. So we're going to use Faraday's law to find the voltage across our inductor. So let me just remind you what Faraday's law was. It was that the induced voltage, I'll call it delta VL because we're talking about an inductor and we're going to use L for the quantity of inductance. That was equal to the change in magnetic flux with respect to time. And again, I won't worry about the sign for now. Okay. So magnetic flux, what's flux in general? Does anyone remember? Yeah, that's exactly right. So it would be something like B dot dA. So if you had some area and you have some field passing through it, the component of the field that's perpendicular to the area, perpendicular to the area, because remember the dA vector is perpendicular to our surface, contributes a large amount of flux. So think of it as the classic kind of description for flux is if you had like a fishing net and you put it into a flowing stream, the stream flows through the hoop of your net. And if you rotate your net so that it's parallel to the flow lines, you get no water passing through the hoop and no flux. But if you keep your hoop perpendicular to the flowing water, you have maximum flux. And so it's the same thing here. In this case, we would take our area to be like the cross section of our cylinder. And the magnetic field is exactly perpendicular to that, so you get maximum flux. So for a single turn of the solenoid, I'm going to call that phi1. So phi is our symbol for flux. 1 is just to remind me that right now I'm thinking of only a single loop in our solenoid. Well, the area of that loop is just going to be A. Like if it's radius r, it would just be pi r squared. And the magnetic field we have right here from Ampere's law. And so that's just mu naught n times I divided by L. Okay, so it's just A times B. But our solenoid, our inductor, is not a single turn. It has a whole bunch of turns. In fact, it has n of them. And so the total flux, we get this contribution from every single coil, or every single turn in our coil. So the net flux for the entire inductor is, okay, so let's see, the total flux is n times the flux of a single loop. And so we're just going to multiply this whole thing by n, and so we're just going to get an n squared here. Everything else stays the same. So it would be mu naught. Let's see, we'll write it n squared divided by L, and then we have an I and an A. Okay. So fair enough, that's the flux. So I'll put a B here just to make it consistent with our notation. And now that's all the hard work. Now we just apply Faraday's law. So we're going to just take the derivative of that flux. Okay, so from Faraday's law, the voltage across our inductor is the derivative with respect to time of this flux, which is d by dt of, whoops, mu naught n squared over L I times A. All right, so that looks a bit messy, but we're going to clean this up. What is the only thing that could possibly be changing with time here? Current, yeah. So mu naught is a constant. A and L are just geometrical factors. So as long as we're not like, I don't know, deforming our solenoid or something, as long as the length and area remain fixed, these are constants. And the number of turns, that's just set by how many windings we make. So those are all constants. I is the only thing that can change. So everything is constant except possibly for the current. Therefore, the inductor voltage is going to be mu naught n squared over L times A at di dt. Now the current may not be changing. We could have a constant current. And if it was constant, this derivative would be 0. So if we have a constant current in our solenoid, there's no voltage across it. That actually makes sense if you think of Faraday's law. Faraday's law says we need the magnetic flux to be changing if we're going to get an induced voltage. And if we have a constant current in our solenoid, it makes a constant magnetic field, which makes a constant flux, and so there's no change in flux and no induced voltage. Okay, so what we're gonna do is we're gonna take everything in these brackets and we're just going to define that to be L, which is the inductance of our solenoid. The inductance of the solenoid. And so therefore, the voltage across our inductor is L di dt. And so there's lots of things that are kind of similar between our capacitor and inductor. Of course, there are differences, but what are the similarities? Capacitance was a constant times geometrical factors. It was epsilon naught A divided by the plate separation D. Inductance is a constant times geometrical factors. So that's similar. And so what we have now is our kind of new summary. First, let's make a note before we write down this new summary. Let's just emphasize that if, let's say, if I is constant, then delta VL is going to be equal to 0. So we get a voltage difference only when I is changing. I don't know why it's so slow. Okay, so we could have I change in a couple different ways. Like you could think of like, you know that if you charge or discharge a capacitor, you get these exponential changes in voltage. The capacitor discharges exponentially through a resistor. We could have a similar sort of situation with our inductor. We could have currents that change exponentially. That's absolutely true, and in that case, you get these voltage differences. But another way you could do it is if we don't restrict ourselves to working with batteries. If we were to power our circuit with the voltage that comes out of the wall, what comes out of the wall? 120. What's that? 120. 120? Yeah, 120 what? 120 volts. So when you say 120 volts, what do you really mean by that? Is it, do you get a constant 120 volts out of there? It's AC, yeah. And so what does AC mean? Yeah, it's the voltage that comes out of here is sinusoidal. So it's oscillating all the time. So if it's at 0 now, it'll go through a peak, come back through 0, go through a minimum. And so it's going from positive to negative through 0. So it's a sine wave. And so what the 120 means is that's the RMS voltage. So if you take your sine wave, it has a certain, okay, you take your sine wave, you square it, you average it, you take the square root, that's 120 volts RMS. So we'll talk about RMS voltage probably in the first lab, actually. But the point that I want to make is that if you have a AC sinusoidal voltage or a sinusoidal current, then that's also always changing. And so there's another situation when you have AC currents in your solenoid, you'll get voltages across your inductor. Okay. So let's just do a little summary. So resistors. Delta VR is equal to I times R, which is R dq dt. Capacitors. Delta VC was Q over C. So let's write it as, I'm going to write it this way. I'm going to write it as 1 over C times Q. And now inductors. The voltage across an inductor is L. It's di dt, but I could write I as dq dt like we did here. And so then we'd have two derivatives of the current. Sorry, two derivatives of the charge. So this would be L d2q dt2. Okay. Good. So what I want to do in the last 5 minutes or so is just think about what would happen if we had a simple circuit that involved a series combination of a resistor, capacitor, and inductor. So let's think about a series circuit with an inductor, capacitor, and resistor. So we'll make a simple one. We'll start with a battery just because that's something we're used to. And so let's say this is V naught, like our battery just supplies some voltage. It could be 9 volts, 12 volts, whatever it is. Okay. And then I'm going to put a little switch in here. So the switch could be open or closed. So this is a switch S. And then we'll have our circuit components in series with one another. Something like this. So this is our resistor. This is our capacitor. And this is the circuit symbol for our inductor. And it's a good symbol because it just looks like a coil. And that's literally what an inductor is. So circuit symbol for an inductor is just this coil. All right, good. And what we're going to do is we're going to imagine that, let's suppose we close the switch up. Before we do that, let's imagine the switch has been open for a really long time. And so the switch has been open for such a long time that there's no current in our circuit, there's no voltage across any of our components. We'll assume that our capacitor is uncharged. If there's no current, there's no voltage across the resistor. If there's no current, there's no voltage across the inductor. So let's start with the switch open so that the current is equal to 0 and an uncharged capacitor so that Q is equal to 0, or equivalently the voltage across the capacitor is equal to 0. So then at time t equals 0, we close the switch. Okay, we don't know exactly what's going to happen right now when we close that switch. Turns out that the behavior can be pretty complicated, but at the same time, we intuitively, I'm going to try to convince you, not today, but another class, that you intuitively do know what's going to happen, and we'll try to think about that maybe Wednesday, we'll see. Okay, so when the switch is closed, when switch is closed, we get a non-zero current. When the switch is closed, I is not equal to 0 and Q is not equal to 0. Because if we close the switch and a current starts flowing, when the current reaches the capacitor, it'll start depositing charge on those plates. And so now we have a capacitor with some charge on it. If we want to analyze this, we would just do a Kirchhoff voltage loop rule. And so we would say start in this bottom left corner, and we just go around and keep track of all the changes in voltage. So the first thing we're going to do is we're going to cross our battery, and it provides a constant voltage. So we just gain the voltage of the battery V naught. Then we're going to cross the resistor. The current is going to go from the positive terminal around in the clockwise direction. If we travel in the clockwise direction in the same direction as the current, are we going to drop or gain voltage across this resistor? Drop. So we're going to have a minus IR. And then if we have current going this way, we're putting positive charge on the top plate. So this is a positive to negative. So we would lose voltage across the capacitor. So we would have minus Q over C. And then we didn't discuss it. We'll probably pick it up next time. But again, if you cross this inductor, you're going to drop the voltage minus L di dt. Okay, so a Kirchhoff voltage loop rule requires that, well, let's see, we gain the voltage of the battery, we drop voltage across the resistor, we drop voltage across the capacitor, and we drop voltage across our inductor. And then we get back to our starting point. And so if we add up all those changes in voltage, they have to add to 0. If we rewrite all this stuff in terms of Q, we would have V naught minus. I'll put this term first because it's already in terms of Q. So I'll write 1 over C times Q. And then which one's next? We'll do minus R dq dt. And then we have minus L di dt or d2q dt2. And so this all has to equal to 0. And this is a differential equation because it involves obviously derivatives of Q. It's actually a second order differential equation because it involves both first and second derivatives. So this is a second order differential equation. And one of the reasons we did all this is because we are going to learn some of the techniques that are used to solve differential equations. We won't explicitly solve the second order differential equation because you'll do a whole course on differential equations. Is that a term 2 course? Yeah. Okay. So next term, you'll do a whole course on this. What we'll do is we'll start with the simpler case of just a capacitor and a resistor, and we'll solve that one. And then I'm going to try to convince you that you already know the solution to the circuit that includes the inductor. All right. Thank you very much.